Hi everyone, my name is Elik. I'm the technical co-founder of Sorry. All right. I'm the technical co-founder of Big Panda. We're a company building automation software specifically for incident management. So we don't automate anything around orchestrating new applications or deploying new applications. What we automate is how we respond to incidents when they happen. And we automate everything from prioritization and routing and remediation. And I want to discuss specifically one area, which is alert correlation. We're not the only company that does that. There are a few companies that does this. And I think we should raise awareness around the importance of alert correlation. I want to start by talking about my background. I worked for 6 years in the Israeli intelligence service. And like any self-respected intelligence service, we processed terabytes of data every minute on thousands of machines. And I recall I have some very distinct memories from my time building systems there. And I think my most memorable experiences there weren't actually related to deploying all those systems at scale. It was actually handling all the different issues and incidents that I was receiving at scale again. So we had thousands of alerts every day, hundreds of incidents every day. And you can imagine very long sleepless nights that resulted out of that. And what do you do when you have a problem of scale? Like you do in orchestration, you automate it. So what we did, we tried to build automation software to automate how we respond to incidents and alerts in the intelligence service. So I have a question for you guys. How many here use automation software for delivery, right? For CI or even config management. So I think the majority here obviously uses the automation software there. How many of you try, even using your own internal tools or using outside tools, try to automate anything around auto remediation? So receiving alerts and somehow responding to them automatically. So I see about, actually not that few, but we have around 20 guys that said they do that. So there's a very distinct division in the world of automation. Like all the tools, the last 10 years was the golden age of automation when it comes to anything related to orchestration, but very few tools, very few disciplines exist around how we can automate anything related to responding to alerts. So this is why I want to talk about that. And let's start with an evolution of a single incident that you might have in your production environment. So this is a timeline of 2 hours. And let's imagine a scenario where somebody, for instance, has deployed, one developer in your team is deploying code that has a very heavy query, a very heavy database query. For some reason, somebody forgot to add an index to the query, and for some reason, the query is very heavy. What are we going to see in it from our monitoring tools? So now we're starting to see alerts, right? So the first symptom we might get is high CPU load on one of our hosts, one of our database hosts. Then maybe another alert on another database host because the application is distributed. We have a huge cluster of databases for our database, and different nodes are beginning to experience issues. Then maybe a critical alert this time for another node, and a couple of other nodes again experiencing issues, right? This is very common. This is what all of us experience often. At this point, maybe our APM, New Relic, AppDynamics, anything you use, might start reporting about high latency issues from my application, right? The queries are taking a long time. They're taking a long time, which means that my transactions are taking a long time. So now my latency is in the hundreds of milliseconds, maybe even in the seconds. So now I'm getting alerts from my APM. Now maybe I'm using a queuing system, right? Maybe all the requests, all the transactions go through a queuing system, like RabbitMQ or Kafka, whatever you're using. And now the queue is becoming bigger and bigger because requests are waiting. They're waiting for the application to process them. So now the buffer that you might have in your queuing system is growing and growing, and your memory is going down. So you're having low memory issues now. And when you have low memory issues, you might also have page faults. So you have high page faults, you have a swap issue. And of course, the queuing system is also a cluster. This is a modern environment, so we have clusters for everything. So another couple of alerts just for my queuing system. And finally, we get the dreaded pingdom alert or whatever alert you're used to happen. When that alert arrives, everything is dead, and your users are actually experiencing the issue, and they can't access your application. So these are a bunch of symptoms, and this is actually a good incident, right? Sometimes we have incidents with hundreds of symptoms not just 10 or 12 like we see here. So this is a different way to look at the same issue. Right? We have this incident concept. This is a logical entity, and this logical entity is composed of many distinct symptoms that my monitoring tool detects. Right? So this incident, whoever is familiar here with the concept of ITIL, there's an abstract concept of an incident, which is basically an outage. Right? I have one outage right now, but I have many symptoms reported by Nagios and Sensu and New Relic and AppDynamics and Splunk and whatever monitoring tool that I might use. And I think one of the problems that we have today is that the monitoring tools are great, right? They're very good at measuring different metrics, configuring thresholds, and reporting on those problems. What they don't do very well, they're not aware of the concept of the incident, right? So it's our role to correlate all the different symptoms. The monitoring tools will not correlate them for us. Now the issue is even worse than that, I think, because any scaled environment has more than one incident or might have more than one incident at any given time. So this actually doesn't look like that. It looks more like this, right? All right, so some kind of an abstract painting. This is the monitoring dashboard of many large companies. You look at their Nagios, and you basically see a circus of red and yellow lights. And a lot of people here might be familiar with this kind of dashboard. So that's a problem. And we interviewed many customers of Big Panda that had this pain of having too many symptoms that happen at once. And there are two main pains or complaints that we hear from those customers. The first complaint relates to response time, right? How long it takes to respond to an incident. So what happens is when I get all of these red lines, it's very hard to identify all the important symptoms that belong to the incident. So I might be getting one high CPU alert on my database, but to understand the full context of the incident, I need to collect all the different symptoms. So I might know that I have high load on one host, but there can be a bunch of reasons why I have high load on that host. What I really need is the full context of, hey, my entire database cluster is having high CPU load, as well as my application has a high latency, and on and on and on. So when you have to slowly collect all those different symptoms, it becomes very hard to get the full context and get back to uptime fast enough. So time to resolution is a big issue when you have so many alerts at once. The second issue is actually time to detection, not just time to resolution. Right? Many alerts fall through the cracks. So what you see in many SRE teams or NOCs that have this problem, what they report is, when I have one host that is down, I don't care about that. I have so many problems right now. I don't care about this one extra alert that I might experience. So the only moment, the moment in which I would actually react to a new alert would be when there's a certain impact to the incident, right? When I get the pingdom alert or when I have an entire cluster that is down. So detection happens very late, right? I don't respond soon enough when I got the first alert that fell through the cracks in this dashboard. So I have a question, maybe anybody who experiences at least one alert in their production environment or their production team experiences at least one alert a day, please raise your hands. Literally half of the guys here. And please keep your hand up in the air if you have at least 5 alerts a day in your production environment. All right, well, how about 50 alerts a day? So we have a few guys here. What about 100 maybe? A few guys here have 100 alerts a day. So some of our customers have 1,000 or sometimes even more than that alerts every day. And the problem of correlation becomes really important. But we see a lot of benefit in correlation even for smaller teams. So one of the metrics that we measure in Big Panda whenever we integrate with the customer is the number of alerts that they generate every day. And what you can see here, the yellow bars are basically the number of alerts you had at a single day. And there's something very clear about this. There is no consistent volume of alerts that you see every day, right? You see a baseline of around 200 alerts. This is a real customer, by the way, from this month of September. You see around a baseline of 200 alerts every day. But then you also see that sometimes you have a bad day, and then you have 1,500 alerts at one single day. So all of us know what this bad day looks like, right? You can't get enough of it. You get 20 alerts, and then another 50, and then another 100. This day doesn't end, and you just wish it would end, but it doesn't. So bad days are very, every company that has a production environment which is scaled and which is complex has those bad days where they have tons of alerts happening. Now, another measurement that we collect from customers is number of incidents that they have every day, right? If we recall the slide around the incident, an incident is basically a composition of many individual alerts that we should correlate together into one context. So the way we collect this incident count is actually based on companies that use some kind of, they have a workflow around managing incidents. So they use maybe Jira, maybe ServiceNow, maybe Zendesk. They use some kind of a tool to record different incidents that they had at any given day. And what we see here is the volume of incidents. The white bars are the volume of incidents they had in any day. And it's very clear that you have about 10% the number of alerts. That's the number of incidents you're going to have. So the ratio is around 1 to 10, sometimes 1 to 20 even, depending on how you set up your monitoring. And I think the thing that's most interesting here is actually not the ratio, not the 1 to 10 ratio, is the fact that if you look at those 2 bad days that we just discussed, what you see in those 2 bad days is that the number of incidents is actually still flat, right? The number of incidents is consistent. It does not go up as quickly as the number of alerts went up. And it took me a while to understand why this happens, why this occurs. And what I realized is that no matter how scaled your environment is, no matter how complex your environment is, actually the number of issues you're going to experience every day is fairly consistent. It's not going to change. It's going to be the same number of alerts day after day after day. What is going to change is the impact of any single incident, right? Some incidents are a result of a DDoS attack. When it's a result of a DDoS attack, all of your alerts are firing up, right? If it's some heavy load on a cluster, the entire cluster fires up. So the real difference between a bad day and a good day is not the number of issues I had, but rather the scale of a single issue or the number of alerts a single issue generated in my monitoring tool. Okay, so how do companies try to solve this issue? Ideally what you would receive, instead of looking at the monitoring tool and seeing all those individual alerts, you would be looking only at the white bars, right? You will see humans should interact only with the incidents instead of the actual individual alerts that are barely symptoms of an incident and not the full picture. So what we heard many companies do, or we've seen many companies do, and I'm sure some companies here still do that, is what we call compound metrics, right? You take a bunch of metrics together and you try to sum them together into one metric on which you alert. So what we have here is a very common example. I have some cluster. The cluster might have 50 different hosts. In this case, I just use 4. And I measure, say, availability. I can measure many things, CPU load, memory. In this case, I measure availability of the host. And a value of 1 means that the host is down. A value of 0 means that the host is still up. I do not alert on any of those individual hosts. Right? I don't want to receive alerts on any individual host that goes down. If I have 60 hosts and one of them goes down, I don't care about that. What I do instead, I average out all the different hosts, all the different values of these metrics into one high-level metric that says what % of my cluster is up or down. Right? If all the hosts are up right now, all the values would be 0, and the average would be 0, meaning nothing is down right now. If half of the hosts are down, then the average would be 1/2, which means that half of my cluster is down. So it's very easy to implement if you're using tools such as Graphite or InfluxDB or Sensu. Most tools have the concept, most metric tools have the concept of aggregate metrics, so it's very easy to configure. What you do once you have this aggregate metric, you configure a threshold that says, alert me once I have enough a fair portion, or I reach critical mass in terms of what part of my cluster is down and I want to alert on it. So this is a very elegant solution, but it has one problem. Any thoughts what the problem might be with this?
No warning? You go straight to, you've got 3 nodes down there out of your 4.
Right, perfect. So late discovery, right? Late detection is the big issue here. What happens is, only when I had 3 hosts that were down, I was alerted on it and my on-call person began resolution. But in reality, maybe even as long as an hour ago, I already had my first symptom, right? One host number 1 was down. I could have already responded to the issue and maybe saved the day, but the only moment that I was alerted is when it might be too late and maybe my users are already experiencing an issue. So this is a nice, elegant solution to reduce the volume of alerts that you might have, but it's not a very good solution if you want to reduce time to detection. So some companies take a different path. What they do, what I call a service hierarchy. So you might be familiar with this kind of tree structure where you structure all your different services and checks in a structure, in kind of a tree, a logical tree. This is a screenshot of a fairly old tool by BMC called BMC Patrol or BMC Performance Center. There are many tools that try to do this, many companies that try to build this internally. What you see here is basically, the top level one is probably just applications, and within every application we have a list of hosts, and within every host we have the list of checks. So this way, we see if we have an alert storms and hundreds of alerts are happening, we can see that at the topmost level of just the highermost application that is affected. So this looks very effective, and you can see the yellow triangles here. This is how alerts propagate up. So if I have a check that is failing, the host will be marked as failing, and then the application will be marked as failing. Two problems with this approach, two big problems, I think. One is it's very hard to maintain this kind of structure in an effective way. Even if you're using automation tool to deploy your environment, it's very hard to make a tree structure that would really make sense to your on-call person or to whoever responds to this. Most applications today are not built like a tree, right? They're not hierarchical in nature. Most applications today are actually more like a jungle of different dependencies. So it's very hard to structure it as a tree, as a logical tree that makes sense. I once interviewed a head of production of a company that had 2 full-time engineers just working on this kind of tree structure and maintaining it and making sure that it still makes sense. So this is one problem. The second problem is white noise, right? If you look at your production, at your Nagios or your whatever is your monitoring tool, you will see that most of the time you have 3 or 4 alerts, just persistent alerts that are there. It's a real issue. Somebody's going to solve it soon. So you always have some kind of alerts in your environment. What happens in this kind of environment, all this, individual alerts, all of them propagate up to the highermost level of the tree, and suddenly the entire tree becomes red, even though we just have 5 or 6 checks that are failing. So if you come to organizations that really do use this, normally you would see just a list of red highermost applications, and when everything is red, it's the same as if everything was green, right? It doesn't matter. I'm blind anyway. If everything is red, I ignore all the red lights. So this doesn't work. If you try this just doesn't work, unlike the previous one, which works but has its downsides. So what I would like to advocate is a different solution around how you can correlate alerts. Again, a few companies right now try to do this. This is what I call stateful alert correlation. So if we look at the 2 solutions we just discussed, what they do is they take a snapshot of how my data center behaves right now, right? They look at all the metrics that I have right now, and they compute the different incidents that I have based on that. So they have no context around what happened so far. They only care about what is happening right now. Stateful alert correlation is harder to implement, but the upside is that it actually has a sense of time. It does look at what happened until now, and based on that, it creates its correlations. And we found that this is a very effective way to correlate alerts. And I think it solves most of the issues we've seen with the other 2 solutions. So let's look at a quick example. The red row at the top is the alerts generated by my monitoring tools, right? These are the symptoms: high CPU, high memory, high latency, number of cursors, anything that is generated by my monitoring stack. And the idea of alert correlation is that users will no longer interact directly with the symptoms, right? I don't care about the symptoms. They are machine-generated items that are generated by monitoring software. I, as a human being, I'm only going to handle incidents. I'm only going to respond to incidents, which are an aggregate of alerts that happen at the top. So alert number 1 arrives to the system. No other incidents right now in the system. What it does, it creates a new incident for the alert. So we have incident number 1 that contains alert number 1. Then alert number 2 arrives. And we try to correlate alert number 1 to incident 1 because it's the only incident we have. And for some reason, our algorithm decides that it cannot be correlated. Maybe different data center, different application, probably should have its own incident. So we create its own incident. Finally, alert number 3 arrives. When that arrives, we do find that it's highly correlated to alert number 1, maybe same application, some kind of heuristic that helps us understand that alert number 3 belongs to incident 1, and we correlate that. And when that happens, we don't have to notify our on-call person right now because he is already handling incident number 1 because it occurred 10 minutes ago. He doesn't have to receive a new page, right? He can only look at the first page that he received. If we take a broader time window, we see how effective this becomes over time. You see, instead of receiving 8 different symptoms or alerts, I only have 3 different incidents. And like I said previously, the actual ratio that we see in real-world examples are 1 to 10, right? Even better than that. So instead of receiving 20 different alerts, you just get 1 incident, and on and on and on. So a quick code sample how this works. Very, very simple. We have to handle a new alert, right? We write a handler for the new alert. Any new alert that arrives, the for loop here basically iterates over all the different incidents that I had and tries to correlate the alert to the incident, right? So the belongs function that you see here is very important. This is a function where the incident says, can I consume this alert or not? If it doesn't belong to me, I say no, and we go on to the next incident and to the next incident until we try to find an incident that is able to consume the alert. If we don't find any, we have to go down to the area where we have to create a new incident for the alert. Interesting, like I said, about 90%, even more than that, of the alerts will arrive at some incident, and we very rarely will reach the bottom block that we see here at the bottom. Okay, how does a UI for something like that looks like? So basically what the user sees, say we have a monitoring dashboard. The dashboard does not show a tree structure of all the green lights that you have. It does not show metrics or anything. It just shows all the incidents that I have right now. And these are real incidents that human beings should consume and understand. And it doesn't matter who you are in the organization, whether you are a developer or a manager or maybe an account manager or maybe somebody on the ops team. You only care about the high-level entities that right now are happening in my environment. In this case, we have high load issue in my database cluster. We have low disk space in my RabbitMQ cluster. We have some connectivity issue in one of the hosts and a data center latency issue in my US East data center. So this is the way we'd like people to look at incidents instead of alerts. Of course, the symptoms themselves are important, right? They help me do root cause analysis and understand the impact of the incident. So once I click on an incident, that's when I finally get exposed to all the low-level alerts that I see in whatever my monitoring tool generated, right? When I click on that, now I deep dive on this specific incident. I say, hey, let's investigate my Mongo cluster issue. And when I start investigating my Mongo cluster issue, I want to look at all the separate low-level alerts that I received from different monitoring tools. And the reality today, when you don't have this kind of alert correlation, what happens is I basically have a very long feed of just low-level alerts, and the correlation is up to me instead of a software. So how is this, by the way, different than stateful alert correlation, where we saw this tree structure? So the important part, again, is that any single symptom depends on the context of what happened so far when we try to decide what it means. So here we have the same alert occurring in 3 different instances, right? Same, let's say this is kind of a packet loss issue that we have on one of my MySQL hosts. First time it happened, I had a ton of alerts, different alerts happening in my MySQL cluster. So I understand that, hey, this is probably an incident related to my cluster. I should address it as a cluster issue that I have, some load issue on my cluster. Then again, I might have another day, 2 days later, I get the same alert, same timeout issue. But this time I have a bunch of other checks failing on the same host. What does that mean? It means that the host is having some kind of issue. Maybe the monitoring agent crashed. Maybe I have a connectivity issue. Maybe I have some kind of performance issue on my host. Different incident entirely, even though the symptom is exactly the same symptom. And then we have the third example where I have some kind of connectivity issue in my main switch. My entire data center is misbehaving. So I get a bunch of packet loss issues on different hosts of different applications, unrelated one to the other, but all of them have the same packet loss issue. Now I know that I have a network issue, right? So stateful incident correlation is very important because it helps me address the same alert in different contexts as they should, instead of just part of the same problem over and over again. Which leaves us with, I think, the biggest problem of this algorithm, and I think the big question: how do you know that an alert belongs to an incident, right? So I was pleasantly surprised, I have to say, that even the most basic heuristics that you would configure here would be very, very effective, right? So if we go back to the, say, compound metrics that we used previously, right, this one. What was the heuristic here? Just clusters, right? We took chef roles, or we took Puppet manifest or whatever, and we said, hey, this is part of the same host group. Let's aggregate its metrics. We can use exactly the same heuristic here, and we can use what I call topology, right? We have some kind of, say, tag. Maybe it's an AWS tag that every one of those alerts has. A new alert arrives, and we ask ourselves, does this alert has the same tag that all of these 4 different alerts had? If it does, it belongs to the incident. If it doesn't, it shouldn't be there. So the worst case scenario will have an incident, an isolated incident for every alert that we already had. So the worst case scenario is what you currently have, no correlation. But in many cases, you'll see when we do have correlation, especially when clusters fall or crash or hosts crash, and then you get an incident for that. So this is one heuristic that works very well, and if you do this, you'll get half the amount of alerts you're getting today. Very basic. Another thing that to consider when you implement a belongs function is time. So something that there's no question about it, it just works. If you look at an alert, if it occurred around the same time that all these other 4 alerts are happened, the likelihood of a relationship is very, very high. If they are 4 hours apart, likelihood of a relationship is much lower. So look for instance, again, a cluster issue that I might have. I have CPU load on MySQL number 1, and 2 days later I have a CPU load issue on MySQL number 2. Probably unrelated, right? 2 separate queries, 2 separate issues. However, if I have 4 different issues on my MySQL cluster, all of them happening in the same 15-minute period, unlikely to be unrelated. 99%, you should correlate them together. So you can combine metrics together. You can use both topology and time to create good correlation. In Big Panda, we use 2 other heuristics, harder to implement, but very useful. One is what we call statistical modeling. So what we do here basically is very similar to what Amazon does when you browse books. You go to a book, and it says, people who bought this book also bought that book. You are probably all familiar with that. So it's very similar. What we do basically is we look at 15-minute periods of your data, and we say, if 2 alerts co-occur at the same 15-minute bucket, the more it happens together, the more related the 2 alerts are. So for example, if I see that whenever host number X, and I don't care about what the topology of my data center is, I just say, whenever host X is having memory issues, I also have latency issues in application B. If I see this happens 5 times in the last month, relationship is very strong, and I can model that very easily. So that's another heuristic that you can use. And the 4th one is human-aided training, right? This is what everybody calls the machine learning or basic machine learning, where customers can vote up or down when you do a correlation. You correlate something, and a user says, I like this correlation, it works well. And then you say, OK, so probably the tags I've just correlated should be counted as related. However, if somebody votes down a correlation, I teach my algorithm to avoid these kinds of correlations. So these are 4 heuristics that we combine together to create a good belongs function. Again, I have to say, while I am recommending you to try out Big Panda, you don't have to try Big Panda. You can implement this in Python on top of Nagios. Just use the top 2 heuristics, and you're already going to get a lot of value out of it. I think that correlation is something that you should consider, especially if you have an issue around alert volumes and noise. Just to summarize, I think I want to end with one note. Like I said, I think the last 10 years was the golden age of automation when it comes to orchestration. I really hope that the next 10 years will be the golden age of automation when it comes to incident management. If you go to serious big infrastructure companies like Google or Facebook, you'll see that they spend a lot of time around automating remediation. And I think it's time that everybody starts experiencing the benefits of using those kinds of tools. Thank you very much. Any questions? Yep.
Have you seen instances where alerts may be correlated with multiple incidents?
Yes, so it's a decision you have to make. You can say one alert can belong to multiple incidents. One incident might be an issue with this host, and another incident might be an issue with this cluster. And this alert, it's hard to say. Maybe it belongs to both of them. So in the for each loop that we saw earlier, you don't have to return, right? You can continue correlating the same alert to different incidents. From my experience, it's better to make a decision, even the wrong one. It's better than confusing customers where an alert might belong to separate incidents. But it's a decision. It depends on the framework in which your ops people work and function. Yeah.
And do you model incidents in different severities, or do you have a relationship between incidents themselves? If a new incident is created, could it be linked itself to another incident?
In what context?
So you mentioned I may have a network failure in one part of the system. That would be an incident in itself. That may then have a knock-on effect with the rest of the platform, because that incident by itself is just an isolated problem. But now your overall load on the rest of your infrastructure is starting to peak because that one data set has gone away. So rather than trying to correlate all of the alerts, that one system goes, well, actually this incident is the reason this other system can't.
Right. So we don't do this. I know that some companies that try to do correlation do. The question was, an incident initially can be an issue with a single host, but then a few hours later I discovered that it's in fact a problem which a much wider scope, maybe it affects my entire data center. Can I evolve an incident and maybe link it to other existing incidents? We don't do this. What basically happens is that one single incident can expand over time. So even though the threshold does depend on time, if we see something happening over time, we do escalate the existing incident and grow it. But probably you can implement solutions where you would automatically link between incidents if they happen, based on some kind of rule or logic. Okay, thank you very much.